manifold, the ambient Ricci curvature in the normal direction. And so, so the idea here is that if phi is complicated, that is, if it changes a lot, then that tends to increase the area. It tends to make the area increase, as you would expect. Whereas if the surface is very curved, that is, if the surface curves a lot, that would tend to decrease the area. So the curvature would tend to cause instability in the variation. And similarly, if the ambient curvature is positive, like if we were working on a sphere, then the positivity of the ambient curvature also causes instability. It tends to create a focusing effect so that minimal submanifolds tend not to be stable. They tend to be unstable. And so that's the general formula. And as I said, I'll talk a lot more about Ricci curvature tomorrow in my relativity talk. But for now, if you don't know the basic Riemannian geometry, you can just assume we were in Euclidean space. That term would just be zero. Okay, and so that quadratic form is associated to, well, just as a symmetric quadratic form, we have an inner product has an associated symmetric linear operator. The same thing is true here. The corresponding differential operator in our called the Jacobi operator. So this is a very basic operator. Minimal surface theory. It's the operator which you get by integrating by parts. So if you integrate this expression by parts, you get minus phi times the velocity phi, and then you can rewrite the second variation in terms of the linear operator L. Jacobi operator. Okay, and in particular, you can see, so this is an linear elliptic self-adjoint operator. So you can see that the number of negative eigenvalues, that is the number of directions, independent directions in which the surface is unstable, is always finite if the surface is smooth. So that number is called the Morse index, the number of negative eigenvalues. And then if the Morse index is 0 on compact sets, we say the surface is stable. It means it's a local minimum for the volume. Okay, and so the important thing, as you can see from the formula about second variation, is that the second variation gives a mechanism which relates the ambient geometry, curvature of the ambient manifold, and also the second fundamental form, the extrinsic curvature of the submanifold, to the behavior, the stability or not, the index of minimal surfaces. And so just for that reason alone, it's extremely important. In particular, that relationship has many applications in geometry. One which I'll talk about tomorrow a little bit is it limits the topology of black holes in general relativity. So it turns out that black holes have a close connection to mean curvature and there's a notion of stability for those. But it has many other applications in geometry as well, this connection. Okay, and so if we wanted to construct, so we talked about the first basic existence problem for minimal submanifolds, which is the problem of minimizing, so we can look for minima. But suppose we want to look for, we're in a situation where we can't necessarily find a minimum, we want to find critical points, minimal submanifolds, which are not necessarily minimizing, but which can be constructed by variational methods. And so generally that's a pretty hard thing to do for the minimal submanifolds, but there is over the years, there's a well-developed theory of what are called min-max constructions. And so the idea is to consider your manifold and sweep it out by cycles. So I've drawn here a manifold which is supposed to be S2, and I've taken a one-parameter family of curves which starts at a point and then they expand up, get bigger, and then they contract to some other point, which could be the same point started with. Okay, and so you can at least intuitively see that there's some sort of non-trivial family of curves which does that, and then you can try to construct an index 1 minimal surface by taking any such family and maximizing the volume in the family and then minimizing overall families. So you would expect then to get a solution whose Morse index is p, at most p. If you had a p parameter family, so here p is 1. And actually, the idea, the theory, the min-max theory of minimalist manifolds also goes way back. In the case of the Douglas disk-type solutions, there's work of Morse and Tompkins in 1940. And then in the 1970s, Tomey and Tromba expanded this work to develop sort of partial Morse theory for minimal surfaces in R3 or Rn. And then Sachs and Uhlenbeck also did very important work on variational theory in curved spaces, Riemannian manifolds around 1980. And in the context of integral currents, actually, the min-max theory was developed in Fred Ongren's thesis, which goes back to the 1960s. So his thesis was about min-max constructions. And actually, for k equals n minus 1, that was the codimension 1 case, Ongren had a student, John Pitts, who developed methods for proving the regularity of the min-max surface. And Pitts was able to handle low-dimensional cases, and Leon Simon and I extended this theory to all dimensions. So the conclusion from that is that if you take any compact Riemannian manifold, you can always find a minimal hypersurface in there, smooth, which is smooth and embedded, a non-trivial one, away from a set of Hausdorff dimension post n minus 8. So in dimension 8 and higher, the min-max surface might be singular, just as volume minimizers are. But they have the same sort of regularity as minimizers do. Okay, and so let me just mention a question which is still unresolved about these min-max constructions in this general setting, geometric measure theory setting, and that is that, as I indicated, as I suggested, if you construct a min-max from sweep-outs by p-dimensional families, you expect the Morse index to be at most p. That's what you expect. You expect the surface to be minimizing in all but p directions. Now, despite the fact that the min-max surface is known to be smooth, say at least in low dimensions, that question is still unresolved for the min-maxes done by these sweep-outs by cycles. And in fact, a recent student of mine, Shinjo, actually solved that problem for metrics with positive reaching, but just for one-dimensional sweep-out. So he was able to characterize exactly what would happen in terms of for the min-max construction. In fact, he showed that either, actually for a simply connected manifold, any such solution would have Morse index 1. Well, if it's not simply connected, then there are just two possibilities: either Morse index 1, or it's a double copy of a stable one-sided hypersurface. So it could be non-orientable. So that does occur in some cases like RPN. Okay, so again, if the ambient manifold has non-negative reaching curvature, then he was able to handle that. But without that assumption, it's still not known, even for one-dimensional sweep-outs. Okay, and so now I'm going to mention in this final part of the second part of my talk, I'm going to mention three fairly recent applications of the variational theory. So the first application is to Ricci flow, and it's part of the proof of the Poincaré conjecture. So, and this uses min-max theory, but for maps of S2 into a 3 manifold. So if we start with a simply connected 3 manifold, we put a metric on it, we can define what Holding and Minikowski called the width. So we can look at S1 families of maps of S2, which are non-trivial families, which generate the fundamental class of M. And then we can maximize the area of the family, and then we can minimize over all such families. And so this should produce. So if we were on the standard 3 sphere, this would produce the equatorial 2 sphere. And so, so in general, we can define, as a function of the metric, we can define the width. So it's called the width because if you imagine a metric where, which looks sort of like a very long thin football, then the width would be quite small. You would expect the width would be the area of that waist surface. So, so it measures the size of the metric in sort of two-dimensional sense. So the diameter may be very big, but the width may be very small. Okay, and so Holding and Minikowski, following the suggestion of Perlman, studied the evolution of this under the Ricci flow. And they were able to show that there's an ordinary differential inequality which is satisfied, which forces the width to go to 0 in a finite time. Okay, and this is an important part of the proof of the Poincare conjecture because it implies finite time extinction. So it implies that the Ricci flow only exists for a finite time, and so there are a finite number of surgeries required to show that M is diffing -3. Okay, so that's one application. That goes back to maybe 2006 or so. Okay, the next one, which is a couple of years old now, is the Wilmore conjecture. And so this is a problem which a priori doesn't look like it has that much to do with area and minimal submanifolds, but it turns out it actually does. So the problem, if we formulate it for surfaces in R3, associates to a surface in R3 its Wilmore energies. This is sometimes called the bending energy. So it's the integral over the surface of the mean curvature squared. Okay, and I put the 1/4 there so that because on the standard S2, H is 2, so that makes the Wilmore of S2 equals 4 pi. Okay, so the Wilmore function is interesting, so it arises from physical considerations. Mathematically interesting because it has a big invariance group. So it's scale invariant, but it's also invariant under Mobius transformations. So it's conformally invariant in a strong sense. And in fact, the sphere is the smallest possible surface for the Wilmore function. That's relatively easy to show going for a long time. Now, the Wilmore conjecture was the problem of understanding the minimizer of this for the torus. So if you consider surfaces which are homeomorphic to a torus in R3, then the Wilmore conjecture says that the lower bound is 2 pi squared, and equality holds only for a specific torus, which is we can describe as a torus of revolution. Of course, remember that any conformal image of that torus would also be a minimizer. But so it's gotten by taking a circle of radius 1 and rotating it about an axis, which is a distance square root 2 in the center. So we take here square root 2, and we got a circle of radius 1. Set at that point, and then we rotate that about an axis, and we get a specific torus of revolution. And the Wilmore conjecture is that torus uniquely up to conformal transformation minimizes the Wilmore function. And the Marquez-Neves theorem solves that in a strong form. So in fact, they can consider any closed inverse surface a positive genus. So it could be a torus, or it could be a higher genus surface in R3. Then they proved that the lower bound is 2 pi squared with equality only for the torus that we described. And the proof is quite involved, but the main part of it is just the use of min-max techniques for higher dimensional families of cycles. So the work that they pioneered here is they found this beautiful application of min-max theory, except not for one-dimensional min-maxes, which normally been considered, but for interesting higher dimensional families. So in their case, the min-max family is actually 5-dimensional. So there's an explicit construction of the min-max family, and then they use the min-max theory for area, actually in S3 to solve the problem. And I won't go into more details of the proof here, but it's I think the paper is maybe 2 years old. Okay, and actually there's a very recent application. Marquez and Neves have extended their techniques involving higher dimensional min-maxes to prove the following theorem. So it says that if you take any compact Riemannian manifold of the dimension between 3 and 7, then it contains infinitely many smooth closed embedded number sources. And so actually, there's a conjecture of Yau that every closed 3 manifold contains infinitely many closed embedded number sources. And so Marquez and Neves solved that for 3 manifolds of positive Ricci, but they also do the higher dimensional case up to dimension 7. So the dimension 7 again has to do with the singularity. Okay, so that's a third sort of striking application of the variation theory. Okay, and so in the final part of my talk, I'm going to talk about maybe a lesser known connection of minimal submanifolds and minimal surfaces with eigenvalue problems. So I'm going to start with minimal submanifolds of Sn. So suppose I take a k-dimensional minimal submanifold of Sn. So it's just the standard round M-sphere, k-dimensional minimal submanifold. Then it turns out the minimality, if I take a submanifold sigma, it's minimal if and only if the coordinate functions, so there are n plus 1 coordinate functions. So this is Sn is contained in Rn plus 1, and so we just think of the ambient coordinate functions as functions on sigma. Okay, and so the theorem, or really the calculation, is that sigma being minimal is equivalent to saying that the coordinate functions are eigenfunctions with eigenvalue k. Okay, so the proof is not hard. It's just if we think of sigma as a submanifold of Rn plus 1, then it turns out for any submanifold of Rn plus 1, the Laplacian of the position vector is exactly the mean curvature vector in Rn plus 1. So that's h in Rn plus 1. Now if we take h in mean curvature in Rn plus 1, we can break it up into the part tangent to the sphere and the part normal to the sphere. Okay, so the part tangent to the sphere is just the mean curvature in Sn of sigma. And then the part normal to the sphere, h dot x, involves the second fundamental form of the sphere itself. And in particular, you can see that it's minus k times x. So that's equal if and only if the mean curvature of Sn is 0. And so the x component here is just the trace of the second fundamental form of the sphere along sigma. And so that just second fundamental form of the sphere is just the metric. And so when you do this trace, you just get the dimension of the space you're tracing over, and with the minus sign. Okay, and so that's a straightforward calculation, which is classically known. So it looks like a sort of coincidence. So okay, so there's, you know, in this special case, minimality is equivalent to saying the coordinate functions are eigenfunctions. But it turns out it actually has a deeper implication, and that is that. So in general, of course, the value k, that is the eigenvalue that you get, it might not be the first one, but let's say it's the peak one. So generally, if we put the eigenvalues in increasing order, we count the number smaller than k, say they're p minus 1, so it's the peak eigenfunction. And so it turns out that if we look at the induced metric on the submanifold, and we consider varying it in the space of metrics, keeping the area or the volume fixed, it turns out that a minimal submanifold, or actually even works in higher dimensions, say a minimal surface, is a stationary point for the variational problem associated with lambdas p of g. So if you consider varying the metric g arbitrarily as a Riemannian metric, the abstract metric, and you look at lambda p as a function of the metric, then the fact that you have a minimal, the fact that it's the induced metric on a minimal surface tells you that it's a stationary point for the variational problem defined by the eigenfunction. So in particular, the minimal submanifolds of spheres play a role as the extremals for eigenvalue problems. So if we consider the problem of fixing the area and minimizing or maximizing whatever we can do an eigenvalue, then the extremals will occur in the class of minimal submanifolds. That's the basic principle. And in fact, the first suggestion of this property goes back to an old paper of Lee and Yao in the early 80s. They showed that when in two dimensions, when k is 2, if that's the first eigenvalue of the minimal surface in Sn, then in fact the induced metric, the metric induced from Sn on the surface maximizes lambda 1 over all metrics in the conformal class with the same area. In fact, they used this to determine the maximizing metric on RP2, which wasn't known before. They were able to solve the eigenvalue extremal problem, maximizing lambda 1 in the fixed area on RP2. Okay, and actually in the middle 1990s, Nataraj really substantially generalized this idea to show that, in fact, any smooth maximizing metric on a surface for lambda 1 arises from a minimal immersion in Sn for some n by first eigenfunction. In fact, he used that to determine the maximizing metric on a torus, that you solve the eigenvalue extremal problem of the torus. Okay, and so in particular, these minimal surfaces in Sn play a special role in eigenvalue problems. And let me just summarize the theory of minimal two spheres in Sn. So of course, the simplest surface is the two-sphere, and so it's interesting to understand the minimal two spheres in Sn. And in fact, the following theorem was proven, I think, in the early 60s by Almgren, but it really uses a method of Hopf. Due to Hopf and Almgren, it uses a complex analytic construction. It's called the Hopf differential. It's a holomorphic differential constructed from the second fundamental form. And in fact, the theorem is that any minimal two-sphere in S3 is equatorial. That is, it's totally geodesic as two. And so that's actually also important in the Marquez-Neves proof of the Roman objection. In fact, there are no non-trivial critical points for S2 in this case. Okay, and if you look at the question of classifying minimal two-spheres in higher dimensional spheres, it actually leads to a very rich and beautiful mathematical theory. So first of all, there are some minimal submanifolds which are actually constant curvature. They're isometric for constant curvature metric from S2 into Sn. And so those actually can be studied using representation theory. So they're embeddings given by eigenfunctions of the Laplacian for a round metric on S2. But for the general case, so actually there are a lot more than that. So for the general case, the ideas begin with a paper of Calabi, and they were developed by many authors in the context of integrable systems. And in fact, there's a paper in the Annals within the last 2 years which answers a question about the moduli space of minimal two spheres in Sn. A question about connectedness for surfaces of a given minimal surface of a given area. So there's still a lot of interesting work done on that. So it's related to Riemann surface theory and complex algebraic geometry. Okay, and so now there's a class of minimal submanifolds which I'm going to talk about in much more detail in the third lecture. But these are minimal submanifolds with boundary, and they have an interesting parallel with minimal submanifolds in the sphere. These are what I'll call free boundary minimal submanifolds in the ball. Okay, so these are minimal surfaces in a ball which are proper, and they meet the boundary orthogonal. Ball, when we think of surface, we require it to meet orthogonal. It's supposed to be E n, this is sigma k. And so one way to motivate this class is if we think of a minimal submanifold in the sphere, we can look at the cone over it. The cone over it is then a minimal submanifold in Rn plus 1. And then if we look at the portion inside the unit sphere, then of course that's one of these guys that meets the boundary orthogonal. But generally, there's a class of minimal submanifolds which have that property. And the reason they're called free boundary minimal submanifolds is because they're the critical points of the volume for relative cycles. So these are critical points where you consider variations which are allowed to move the boundary but preserve the volume. So you consider variations, they don't fix the boundary, they move the boundary, but they vary along on the boundary. The variations are tangent to the sphere. So that's a very natural variational problem, which has also been studied also by Almgren and many other people. So we're going to look at the geometric aspect of that. So it turns out that those submanifolds also are related to an eigenvalue problem, and so in that case, the coordinate functions. So if I have a sigma k and dn, they're n coordinate functions. They satisfy the condition that in the interior they're harmonic because the surface is minimal in dn. So they're harmonic functions in the interior, and they satisfy the boundary condition, which is so the co-normal vector, that is the outward unit normal for this, is the position vector. So eta here, my x, eta is x. And so when I take the normal derivative of the position vector, I'll just get the position vector back because eta is just x. I'm just differentiating in the direction of the position vector. So in particular, these satisfy the harmonic inside that satisfy this condition. So this turns out to be an eigenvalue problem, which actually is also much studied in different contexts, particularly in applied mathematics. And it has to do with what's called Steklov eigenfunctions, eigenvalues of the Dirichlet and Riemann manifold. So generally, if we take a manifold with boundary, in cases submanifold sigma, then we can look at the operator which takes a function u on the boundary to a function u on the boundary where L of u is the normal derivative of the harmonic extension. So we can take a function on the boundary, we can extend it harmonically in the interior, solve the Dirichlet problem, and then we take the normal derivative, and that defines an operator on the boundary. So actually, if you do this in the upper half space, so you take the manifold from the upper half space, it's the square root of the Laplacian. So it's a square root of the Laplacian. So it's a global operator. It's a pseudo-differential operator. You look at pseudo-differential operator, and you can see that the eigenfunctions for a free boundary surface are Steklov eigenfunctions with eigenvalue 1, right? Because the condition they satisfied was that the normal derivative is the function itself, the harmonic inside, and the Neumann data is equal to the Dirichlet data. So that's the eigenvalue problem. And then in the third lecture, I'll explain why these free boundary minimal surfaces represent extremals of Steklov eigenvalues. They're the extremal configurations you get when you consider usually maximizing them in eigenvalue. Okay, so I've introduced. So I started with minimal manifolds of the sphere in connection with the ordinary eigenvalue problem on closed surfaces, and then now I've talked about surfaces with boundary and free boundary solutions and associated eigenvalue problem. And now I want to I talk about the theory of two spheres in Sn. I want to talk a bit about the theory of free boundary minimal disks in Vn, which would be roughly the analog of that. So there's again a relatively old theorem, it goes back to 1985 by Nietzsche, which is again the analog of the Almgren theorem, the Hopf-Almgren theorem. So it uses the same basic Hopf construction, so it uses complex analytic methods, and together with the boundary analysis, of course, sort of boundaries do that. So the consequence of Nietzsche's theorem is that any free boundary minimal disk in V3 is a flat disk. That's true. So then the question is, what happens for n greater than or equal to 4? Okay, so if you, based on the analogy of minimal two spheres in Sn, we would expect that there may be many such solutions of that problem. Okay, and so it turns out, however, that there are. So this is a recent result with Fraser. So it turns out that actually any free boundary minimal disk in Vn for any n is actually a flat disk. So you might expect that you could use variational methods or integral systems methods or something to construct non-trivial disk, but in fact they aren't. So in that sense, this free boundary problem is more rigid than the case of minimal S2s in Sn. And so let me give a rough outline of the proof. Again, it's a complex analytic proof. So we're in higher codimension. Of course, the codimension in one case is solved by Nietzsche. And so, but if we consider a conformal parameterization of such a disk, we call it phi from the map from D of Vn, and it's conformal. Okay, and so let's take Z to be the complex coordinate of the disk. The conformality relation can be written in complex form. This means the partial of phi with respect to Z. And this is just the dot product for complex valued functions. So it's not the Hermitian product. It's an indefinite quadratic, indefinite scalar product. And so that condition, phi z dot phi z is 0, simply encodes the conformality condition. So that's automatically true for conformality. Okay, and then the Hopf differential construction, if I write it in complex form, amounts to this. So if I take this expression, so phi zz is, now I'm thinking the vector valued function, two derivatives in the z direction, and then I take the normal component at the image, so that's a second fundamental form term, then I multiply that by dz squared, I get a holomorphic quadratic differential. Well, it's holomorphic with respect to the normal connection. So it has values in the normal vector fields, but of course there's an induced connection on the normal bundle which defines a complex structure on the normal bundle, and it's holomorphic in that sense. So it's a vector valued holomorphic quadratic differential. Okay, so it turns out the free boundary condition implies that normal vector valued 0,2 tensor phi is real. It's real when you evaluate it along the boundary tangent. So you think of the 0,2 tensor as a quadratic function of vectors. When you evaluate it along the tangent vector of the boundary, it has real values. It's a real vector value. So that follows from the free boundary condition. And then what we can do is we can make a complex valued quartic differential by just squaring it. So we take phi dot phi, so we use the dot product again to square it. When we do that,